Okay, everybody, here we go. Chapter 7. We're going to look at the standard normal curve today. This is a long, I know I've said this before, this is a long slide. I think there's like 34 slides, so maybe going to be a little bit of a longer video. We'll see. So first we're going to look at using the probability density curve to describe a population. We're going to use a normal curve to describe a normal population, finding the areas under the standard normal curve, and finding the z-scores corresponding to the areas under the normal curve. First, we're going to take a following figure presents a relative frequency histogram for the particulate emissions of a sample of 65 vehicles. If we have information on the entire population containing the millions of vehicles, we could make the rectangles extremely narrow. You see how tiny the rectangles are here? The histogram then would look like a smooth and could approximate it, and could be approximated by a curve. So what they're saying is if these were all small, it would look more like a curve. The curve is used to describe the distribution of this variable is called a probability density curve of the random variable. The probability density curve tells what proportion of the population falls within given intervals. The area under the probability density curve between any two values of A and B has two interpretations. The area is equal to the proportion of the population with the values between 3 and 4, or alternatively, it represents the probability that a randomly selected value from the population is between 3 and 4. The region above a single point has no width, thus no area. Therefore, if x is a continuous random variable, so the probability of x equals a, would equal 0 for any particular number. That means that x would have to be greater than or less than b, would also be greater than or equal to and less than or equal to b for all numbers a and b. In other words, doesn't make any difference of whether you include a and b or not. For any probability density curve, the area under the entire curve is 1. Now, the probability density curves come in many varieties depending on the characteristic of the populations. Many important statistical procedures can be carried out using one type, which is called the normal curve. A population that is represented by a normal curve is said to be normally distributed and to have a normal distribution. So when you hear that, you will see this. The population mean determines the location of the peak of the normal curve because remember the mean and the median are both in the center. The population standard deviation measures the spread of the population. Therefore, the normal curve is wide and flat when the standard deviation is large, and tall and narrow when the standard deviation is small. So here we have the mean being at 0, the standard deviation of 1, and here we have the mean being at 0 and the standard deviation of 2. You can see it spread it out more. The mean and median of a normal curve are both equal to the mode. So they're all equal in a normal curve. Now we look at this before. We have 68, 95, 99.7. 68 is 1 standard deviation away from the mean. 95 is 2 standard deviations away from the mean. And 99.7, which they said before was almost everything or almost all, 3 standard deviations away from the mean. So let's find the areas under the standard normal curve. A normal distribution can have any mean and any positive standard deviation. However, the normal distribution with a mean of 0 and the standard deviation as 1 is known as the standard normal distribution. When finding the area under a standard normal curve, we use the letter Z to indicate the value on the horizontal axis beneath the curve. We refer to this value as the Z-score. Since the mean in the standard normal distribution is 0, the mean has a Z-score of 0. Points on the horizontal axis to the left of the mean have negative Z-scores, and points to the right of the mean have positive Z-scores. This may be used to find the area to the left of a given Z-score. So if we have a table, and you can find these tables, you can Google these tables, you can look in the back of every statistics book and find a table, and this will help you find the area to the left of a given Z-score. So here's our Z-score, and anytime we're looking up this value, the area underneath is always to the left. So let's find the area to the left of 1.26. We have a normal curve. We know 0 is here. The label point is 1.26 would be here. Shade the area to the left of it. Look at the table. Look up 1.26. We're going to find 1.2, and this is our hundredths digit. Go over to 6, and this will give you your area. The value of 0.8962 is the area to the left of 1.26. If you want to find the area up to the right, you're going to sketch the curve. It's negative. Remember, 0 is in the middle, 1 standard deviation away, so it's going to be about here. Negative 0.58. Now, the table gives us to the left. So what we would do is we would look up that 0.58. This would be the area to the left. So how am I going to find the area to the right? I'm going to find the complement. So I take 1 minus this value, and it will give me my area to the right. What about between two numbers? If you think about it, if you look up this value, you will find the area to the left of this. And then you look up this second value, negative 1.45, and you'll find the area to the left of it. If you subtract this minus this, you'll have what's left in between. So here we have subtracting the smaller area from the larger area to find the area in between. We have our Z-score of 0.6628 and our Z-score of 0.0735. We subtract the two. I'll be subtracting this from this, and it'll leave me with this area of 0.5893. We can use our calculator to do this too. The normal CDF command is used to find the areas under the normal curve. 4 numbers must be used in the input. The first entry is the lower bound of the area. The second entry is the upper bound of the area. And the last 2 entries are the mean and the standard deviation. So finding the area left of 1.26, there is no lower endpoint. Therefore, we're going to use -1 E99, which represents -1 followed by 99 zeros. We select the normal CDF command and we enter this is as the lower point, this is our upper point, 0 as our mean because it's in the center, and the standard deviation of 1. When I hit enter, I will get my area of 0.8961652533, which we will probably round to 4 places. Finding the area to the right of -0.58 again. If I'm going to look at to the right, my lower value is going to be 1 with 99 zeros after it, or that's my upper value. My lower value is -0.58. My upper value is 1 with 99 zeros after it. Again, mean and standard deviation are the same, and I will get my 0.7190427366, which again we would probably round to 4 places past the decimal. And between 2, well, now we're going to use our lower as -1.45, our upper bound 0.42, our mean and our standard deviation, and then we get our 0.58922799372. So doing the one that has a lower and upper bound with your calculator seems a lot less complicated. Looking for the z-scores corresponding to the areas under the normal curve. We have been finding the areas under the normal curve from the z-scores. Many problems require us to go in reverse direction, so if we're given the area, we need to find a z-score that corresponds to that area under the normal curve. So find the z-score that has an area of 0.26 to its left. Sketch the curve, mark the area. Now we're going to look through the body of the table for the number that is closest to that. And this value, 0.2611, is closest to 0.26. So I will go up and I will see there's my hundreds place, my tens place, and it's negative. So my z-score would be -0.64. What if it has the area of 0.68 to the right? Well, I would sketch a normal curve so I can have a visual here of what I'm looking at. Then I would take 1 minus that value because it will give me the number that I need to look up in my table, which gives me my area to the left, 0.32. Go as close as I can find on here. 0.3192 is closer than 0.3228. So you want to go the closest, which is this one. Hundreds place is 7. -0.47 would be the z-score. What about the middle 95% of the area under the normal curve? We should know this one already. We're going to sketch normal curve, shade in the given region. To the left, Z1. To the right, Z2. We're looking for an area of 0.95. Since the area is the middle part of 95%, the two tails on the end would combine 0.5. Half of that would be, one of these ends would be 0.025. So now I have this value and this value. So if I look at the table, oh, it didn't give me the table this time. The area 0.25 corresponds to z equals negative 1.96. The area to the left of z2 is 0.9750. This could also have been found by using symmetry. Knowing that I get this, I could know by using symmetry, I could say it's 1.96. Either way. Finding z-scores corresponding to the areas under the normal curve. Oh, we already did this. Maybe this is a double. Oh, nope, this is going in reverse. Okay, so we've been finding areas in a normal curve. Now let's see how we do it with our calculator when we're given the area. This time we go to its INV norm, kind of like inverse normal. Calculator will return the value of the normal population with the given area to the left. Find the z-score that has an area of 0.26 to the left. We're going to hit INV norm command, enter 0.26, and we will get the area under the curve is approximately negative 0.64, our z-score. Okay, so our z-score for right here, or our z number right here, is negative 0.64. Let's find the z-score that has an area of 0.68 to the right. That means it would have 0.32 to the left. So I can hit my inverse norm and I have 0.32 because this gives me the number that will be when I find the area to the left, and I know that to be this. Again, we have our mean and 1 is our standard deviation. And when I hit enter, I'll find out that this point right here for my z value is negative 0.46769888012, probably rounded to 4 places past the decimal, making this a 7. Find the z-scores that bound the middle 95% of the area under the curve. Sketching it again, knowing that this is 95%, leaves 5% left here. So we're going to split that 5%. We'll get 2.5, which means if I want to take a look at this number, I could put in the area to the left that has 0.975, or I can also put in my value from here down, and let's see what they do first. All right, so they use that 0.25, and you get negative 1959963, etc., rounded to 4 places past the decimal will give you negative 196. That gives you this number here. And we can say by symmetry, then we know that this would be positive 1.96. Or we can do what we said before, which is replace this value here with 0.975. And it'll give you this whole thing. And then that will also give you the 1.96. Okay, well that actually went a little faster than I thought. Hopefully not too fast. You can always stop the video, go back and review. Email or text me, let me know. Today you should learn how to use a probability density curve to describe population, how the shape of the normal curve is affected by the mean and standard deviation, how to find areas under the normal curve, and how to find the z-scores corresponding to the area under a normal curve. Okay, next one will be 7-2. See you soon.